Okay, today we will start with analysis of single phase induction motors. Last class we initiated the discussions in which we found out that the single phase induction motor will have a single phase winding in the stator and a squirrel cage rotor, and once you pass a current through the stator winding, the alternating current, it will lead to a fluctuating field in the air gap, right. So, the air gap is not rotating, the air gap field, but it will be varying in time, but the axis will be same, right. So, that is the concept we had, and they typically have we will now like to see how you can resolve these fluctuating or pulsating fields. Okay. For this we have seen it carries a AC current in the windings, and then this field, air gap field, we said can be represented by a statement, that is, it will be varying in space and varying in time. Okay. And if you have a conductor carrying currents like this, we said that it carries a current I. Last class we said, of course, with the squirrel cage rotor, we said it will always be axis of the field will be like this, right. This will be the field F, and the field F with reference to theta, okay, will be like this. Of course, if you take theta is equal to 0 here, this is pi, this is 2 pi, okay, and this is represented by that expression, that F equal to some F max cos theta cos omega t, isn't it, where this is the F max is the peak of F at I equal to I max, because we also can say that the current is varying in time like this as a function of omega t. Current is changing with time. Current in this one is a function of time, sinusoidally varying, okay, and with a peak value here of this I max. So, you can always say I equal to I max cos omega t, and we have seen that the MMF will be as a function of theta and t will be following this pattern. Okay, that will be the MMF in the air gap at any position theta. See, this is, if you say theta equal to 0, so you can always have any position theta. I want to know what will be the air gap MMF, okay, at that position theta. Is it okay? So, we have always said it is like placing a magnet here, which whose magnitude or a strength will go on changing with time, but magnet will not change its position. Okay. This is the concept. In the, if you look at the air gap, a single winding excited with AC, this is the picture that you have. Okay. And we also, you have at any position, at any given position, there is an MMF, but that will also vary with time. Any position theta, the MMF or the magnet of MMF is what? It is the potential between the stator and rotor surface. That potential goes on changing with time. Okay. And we could write that if this is theta equal to 0, this is t equal to 0, and then we said omega t is equal to this is pi. So, omega t is equal to pi by 2, where what will be the MMF? Huh? What is omega t is equal to pi by 2, that is at this position, at this instant of time, it will be 0. That means it will have a, that means this will be the picture. Okay. That means at that instant when the winding current is 0, stator and rotor MMFs are at the same potential. Stator and rotors, they are at same potential, there is no potential drop between them. So, it is 0 potential, as if it is non magnetized, it is very simple. Okay. Now, when you go to this position pi, omega t equal to pi, this is 0, omega t pi, what happens? It will have a mirror reflection of the same thing. Okay. So, you may have a situation where it will be right. So, this will be at omega t is equal to pi, and this is pi by 2, and 3 pi by 2, and this is omega t is 0, and this also same is omega t is equal to 3 pi by 2. So, it will follow the same. Then at 2 pi, at 2 pi it will go back to the same point. Okay. So, it will follow the same point, this is at 2 pi. So, in between maybe pi by 4 or something, it may have a you can similarly plot some other instant, okay, and you can also plot for some other instant, right. So, you will notice that it will follow different peaks, is not it? Peak will be there only, but peak will magnitude will not be same, okay. And at different positions of theta, it will have a different amplitude of the MMF, and that, so if you take this theta, it will have this MMF at time t equal to 0, there is some other MMF at 45 degrees, 90 degrees, like this, right. Is it clear? Any doubt? So, obviously, you are having a magnet whose strength is changing with time, but axis is not changing. Okay. So, peak value will be there, but at every position of the air gap, it will have a different potential at different instants of time, which would we always say that the air gap MMF is therefore a function of space and function of time. Okay. So, how do we analyze this? That is the next question. Okay. So, you can write that expression can be written as half of f max is a trigonometrical this thing. So, it have two components, one has a half theta minus omega t, another will be half theta plus omega t. Okay. So, you can always write that f theta t is half of f max cos of theta minus omega t plus half of f max cos of theta plus omega t. So, what you have done here is purely a trigonometrical resolution. Okay. So, cos A cos B is cos A minus B plus cos A plus B, is not it, half of it, right. Now, this each of this represents a different type of field. What will this represent? Cos theta minus omega t, what will this represent? Magnitude is same. What it represents? It is a rotating field. So, this is called, this is a forward rotating field, and this is backward rotating field. Right? One is a forward rotating field and a backward rotating field. Okay. So, you represent this is a positive or travelling wave or a forward wave. Okay. Another negative travelling wave or a backward wave. What is the nature of these fields? Look at each of these. So, F plus and F minus the air gap field. So, this one is because it is a fundamental. Okay. We are neglecting all space harmonics, right. So, what we have done is assumption is neglect space harmonics. What do you mean by that? You assume that the MMF is sinusoidal in space, although it is not. It will have its own MMF wave may be trapezoidal or it may be non-sinusoidal. So, if it is non-sinusoidal, there will be harmonics. So, we neglect the space harmonics. Space harmonics means it will have more number of poles. Fundamental have only 2 poles, third harmonic will have 6 poles. Okay. That is what is meant by space harmonic. In the air gap, space, that is what, but we neglect that. Okay. So, neglect space harmonics. So, what is the nature of these fields now? Let us say nature of forward field. What is the nature of forward field? We have written as F plus will be half of F max cos of omega t minus theta. This is one field. What does it mean? So, its amplitude equal to half F max, right. That means, I have now have one magnet which will always give a MMF of half F max on its axis. So, what you have got is I have a magnet which here at this position it will give you half F max, and of course, it will be sinusoidal. Okay, it is sinusoidally. So, here it will be 0, here it will be 0, and here it will be minus f max if you place the magnet. This is one thing we have got. Then what else we have? So, we have its amplitude is half f max. Then what is the other thing? So, we have taken care of this. What does the other part indicate in physical terms? Frequency of rotation is what? Omega. So, you have frequency of rotation is omega unit. Omega is what? What radians? Electrical radians. Omega electrical radians per second. So, it is rotating at omega. This magnet is not standing, unlike in the earlier case where we have kept the magnet standing. Magnet was not rotating at all, but amplitude was changing. That amplitude of the magnet was changing. So, here my amplitude is not changing. So, we have amplitude not changing, but magnet is rotating at omega electrical radians per second. Amplitude is same, half f max. So, one field is rotating field at omega electrical, that is, this becomes this is what we call it as synchronous speed. And synchronous speed, you know, ns will be synchronous speed 120 f by p, isn't it? Right, because you know so many rpm. So, it will be rotating at 120 f by p, where f is the frequency, f is omega by 2 pi. Though it's very fundamental to you, I think it is necessary for you to understand. Is it okay? This is about the forward field. So, similarly, you can easily say that what is the nature of backward field? You can always say amplitude is half f max, same amplitude, half f max, and speed, what is the speed? Minus omega electrical radians per second. Because here you have omega t plus theta, theta plus omega t. So, this is the backward field, that means runs at omega in backward direction. What do you mean by backward direction? What do you call it as a forward direction? Clockwise, anti-clockwise is one. They are opposite to each other, but which one is positive, which one is negative? Anything can be positive, anything can be negative, right? But there is in motors we have to have some specific things, no? Otherwise you get confused. Directional rotation of rotor. Okay, forward is, so we have a convention. So, forward is in the direction of rotor, in the rotor direction. Because rotor always rotates, say rotor rotates at say omega r radians per second, isn't it? So, this is rotor speed. Rotor speed is omega r electrical radians per second. okay, or ns or nr or whatever you may say. Now, that will be, therefore, if you look at the rotor, so here is the f plus and here is f minus, and the rotor itself rotates omega r, and this rotates omega, this rotates omega. Okay. But rotor is rotated omega r, so it reacts one way to the forward field, other way to the backward field. What will be relative motion? See, in the forward field there will be a small slip, but backward field it will not, it will be, slip will be more, right. Okay. We will know that here if this slip here with the forward field is s, here it is a 2 minus s. It is easy to find. Now, what we notice here is, therefore, we a pulsating field which is stationed here, okay, is resolved into, because its amplitude of course is f max. What we say is it is split it into half, okay, half f max this is also half f max. Earlier I had only one magnet which varies from f max at time t equal to 0 to minus f max at time t equal to or omega t is equal to 180 degrees. Now, what it physically means, now we are saying this fellow is rotating forward, so it will go this way. So, this will be at omega t equal to 0. Okay. Now, what will happen at omega t equal to 45 degrees is equal to pi by 4 say. So, it shifts because it has moved forward field. So, this vector which was here, which has moved here, and this vector which is moved back, let us say, okay, I will call it different. So, this backward at t equal to 0 are same, they are aligned, omega t is pi by 4. So, my magnets are at this, at 45 degrees, my magnets are now located here. So, one magnet here, one magnet here. Therefore, what will be the resultant of this will be net magnet is somewhere here, right. Okay. Which will not be, so earlier it was f max was here, now it will be, the maximum is not f max, it is less than f max, but that you can have, how much will it be? At 45 degrees? So, you but this is basically you have to find out. So, this is 45 degrees, it will be 2 root. How much? F max by root 2? Okay. So, at 45 degrees here by root 2, 1.4 or something like that. Okay. Then you can also try at 60 degrees. Pi by 3, okay, and then you come to omega t is equal to pi by 2. You come here, magnet has come here at omega t equal to pi by 2, and same magnet has now, the backward magnet has come here. Okay. So, at 60 degrees it will be half of this, is not it? Okay. It will be cos 60. So, this will be pi by 3, pi by 4, pi by 3, then pi by 2 it will be here, okay, it's pi by 2, right. And then again maybe after 30 degrees it will go here. So, it will be 210 degrees, 180 plus, okay, here, and again you can resolve the same thing to again 45 degrees. So, it will be what pi by 2 plus pi by 4, this will be 5 pi by 4. So, it will have a mirror reflection of this. This will be pi by 4 here, then pi by 2 here, is okay. So, you can repeat the same thing. This will be at 180 plus 30 degrees, and then yes, what will be this? It will be 6 pi by 4 or 3 pi by 2, okay. So, this is sorry, this will be pi. At pi what is happening? One magnet is here and other magnet is here. So, this is at pi. So, net is here. So, you will see that it will assume different positions, the forward magnet, one was here, here, then here, okay. But you will see that the axis of the resultant will not change, okay, it will go on. So, a pulsating field is resolved into two rotating fields, okay. Therefore, we come to say that pulsating field equal to sum of two rotating fields. Okay. So, that is one rotating at plus omega, another rotating at minus omega. This is forward, backward. Any doubt at this point? So, what we have done is, imagine there is a magnet which is changing its strength with time, but the magnet is not changed. That is equal to, you have take two magnets equal to the half of the amplitude of the original magnet, and one rotate forward and the rotate backward, synchronism, so that the net resultant will always be along the same axis. So, we can now say, like similar to a superposition, we can analyze the single phase motor as a reaction to each of the fields. Okay. So, we can say that a single phase motor can be analyzed as superposition of reaction to each field. Is it okay? So, what I do is, I only take forward field and analyze, then I take only the backward field analyze, and then what we do is, we sum up these two responses and say this is the cumulative response of the motor due to the both the fields together. Any doubt on this? Okay. Therefore, we are having one forward rotating field and another backward rotating. Okay. Now, at starting, forward field is of having same strength as a backward field. See, at starting there is rotor is not moving at all. So, it will react same way, because as far it is concerned, one is forward, another is backward, it reacts the same way, is not it. So, it is like somebody is pushing in one direction, other is pushing in the other direction, but the fellow does not move. So, net torque experienced is 0, right. It is like you take a shaft, in one you push the same way in one direction and simultaneously push the same way in the other direction. So, forward torque and backward torque will be same. Therefore, you will find that at starting at speed equal to 0, here is the shaft. So, it will experience a forward torque, it will also experience the backward torque, okay, at the same time, because net torque will be T is equal to T forward minus T backward, because T forward equal to T backward. Therefore, this is 0, right. Forward torque is same as backward torque. So, this is a very simple physical explanation, right. So, you look at the field and the field will be the same direction. So, this is one thing we can have. So, it does not, one of the important thing, unlike in a 3 phase motor, a single phase motor does not have a starting torque. Okay. This is a very simple physical explanation. A single phase motor does not have a starting torque, okay. And all the developments, engineering developments have taken place over last several decades. Initially was how to start. So, unlike in a 3 phase induction motor where there is no starting problem, you apply the voltage, it starts. Here you on its own it will not start, okay. So, that is the basic issue here, okay. Of course, if you give a torque, if you give a spin it, then if the speed becomes non-zero, then the forward field becomes stronger than the backward field. So, positive negative they do not have the same magnitude. So, if you spin it in the forward direction, it will rotate in the forward direction. If you spin it in the backward direction, it will rotate in the backward direction. So, all you need to do is, it depends upon which direction you spin, okay. So, motor will start rotating and goes to its equilibrium position as it. So, it experiences a torque, okay, and it will go on rotating till the load torque is equal to the developed torque, isn't it. Okay. So, what is the assumption we have made so far? In this hypothesis, we said that the forward and backward rotating air gap fields are equal at all speeds. Air gap field, forward air gap field, after all, where is the field? The field is in the air gap, okay. In the air gap, what we are assuming is this is the forward field, this is the backward field. I will say this F, this is B, both are of same strength, okay. And then there is a forward rotating flux, there is a backward rotating flux, and each will react. So, what has been done is, forward flux, this is like in a 3 phase motor. So, it will give you F, F is the forward. If you want to write the torque speed characteristics, you are very clear that we have the one, this is a normal 3 phase motor, which is due to the forward field. So, normal supply you give, it will give this, okay. Then then for the backward what you do is, you change the phase sequence, of the windings, apply the same voltage, but change the phase sequence, and then it will follow this curve, the backward. So, this is due to the F field, this is the B field. Okay. This is F field and this is the B field. One is the forward field, you apply a voltage, say if it is okay. Then other side what you do is just reverse the phase sequence, and then cumulatively you have this resultant field, resultant torque. So, this was let us say Tf, this was Tb, and this was T. In this case, because Tb is written as opposite anyway, is effectively Tf plus Tb, cumulative effect, is not it? I have already written Tb in the negative direction. So, at every point you see what is the torque, and normally the forward torque is more than the backward torque at any speed other than the starting. At starting, the forward torque is equal to the backward torque at starting, but at negative speed what will happen? Negative speed, this backward torque is more than the forward torque. So, the shaft is subjected to backward torque, okay, and you can go up to this so called near synchronous speed. So, this was the initially the hypothesis from which single phase motors were analyzed. Okay. So, this is equivalent to what? So, how do you get this total characteristics if you are given a single phase motor of certain windings, etc. So, you can assume what you are doing is I have two motors M1, M2, okay. You couple them together. My single phase motor equal to two motors. So, what you do is there is a 3 phase supply anyway. There is a 3 phase supply and you have 3 phase windings. Okay, let us say ABC. Let us say the two machines identical A1, B1, C1. Let us say A2, B2, C2. Okay. I mean assuming they are all, so you let us say star connect this. Now, if this is the supply points A, B, C, you would normally connect one machine A, B and C, okay. Normal. This is the forward motor, okay. So, that is what you have. Then the second one, let us say you connect A, but this B you connect here, okay, and C you connect here. Is it okay? So, this is a backward motor. Is it clear? So, so this will be equivalent to a single phase motor. The single phase motor is equivalent to this. So, instead of applying only one phase voltages, you try to see that the voltages are divided into half per phase and you apply this 3 phase supply. Okay. Is it clear? So, this is what was conceived as a correct way of looking at a performance of a single phase induction motor as equivalent to cumulative effect of 2 3 phase motors of appropriate amplitude of voltage applied, but you apply to two motors in a which are opposite phase sequence. One will be producing a torque in one direction. So, one will be T, this will apply, supposing this is the rotation. So, there may be one Tf and another will be Tb, right. So, net torque will be the cumulative of these two, and the currents also. So, the net current also will be the sum of these two currents, right. So, this was the concept, right. So, it will produce a forward flux, this will produce a backward flux in the air gap. So, one motor will have a forward flux in the air gap, but these fluxes are same, forward rotating flux is same as the backward rotating flux. Okay. Forward rotating flux equal to backward rotating flux. That is how it was analyzed. Okay. You are clear up to now how it was done as a 3-phase motors. Okay. And they said this is the way to analyze a single phase induction motor. Okay. So, how do you analyze single phase induction motor? Take 3-phase motors, connect them one forward, other backward, cumulative, and you analyze. So, then you write all the equations and solve them, and everything can be done. Okay. Now, I will tell you all the logic I have told so far, okay, and the whole statements which I have made so far, everything is wrong. Whatever I told till now is wrong, I have fooled you. Okay. So, the assumptions whatever we have done is wrong. Okay. But you went on assuming whatever I told was right. Now, I am telling whatever I told was wrong. Why? This was a wrong assumption. What was the wrong assumption? That forward air gap field, forward rotating air gap field is not equal to backward rotating air gap field. This is not the correct assumption. Is it okay? So, think about it. I have made this statement. Till now I made the statement, they were all same, forward rotating flux is same as to backward rotating flux. So, this is what you assume, but the factor, because when you connect two motors, one positive and one negative, the forward air gap flux is equal to backward air gap flux. Now, you have to be little more cautious whenever we take a word field. We always talk of field. What is a field? What do you mean by a field? What is a magnetic field? See, we always talk of course, there are a lot of fields, we also talk of magnetic field. What is a magnetic field? Right. Now, the field has different quantities. We have B, we have H, we have phi, you have F. These are the terms we use for in denoting a magnetic field. What is B? Magnetic flux density, and what is H is magnetic field intensity. The H is the one, magnetic field intensity, and B and H are point functions. At every point there is a B, at every point there is a H in space, and B and H are related equal to, is not it? That depends upon the material properties, the mu. Okay. So, you have got B and now similarly you have a phi. What is phi? Is the flux, and this you call it MMF. So, forward rotating field is a very misnomer. What is it, that field? Is it a flux which is rotating, or is the MMF that is rotating? Okay. What is rotating? Are both rotating? In the air gap, what do you mean by rotating field? Huh? Okay, MMF rotating. Flux not rotating? Is area flux not rotating, or is stationary? When you say synchronously rotating field, what do you mean by that in the air gap? It is rotating at synchronous speed. What is rotating at synchronous speed? Some human being rotating? Are some electrons rotating? Okay. At every position there is a magnetic field. Okay. There is a B and a H and a phi, and BH are point functions, where phi is not a point function. Is phi a point function? When you say flux, flux is not a point function. MMF is not a point function. I mean, a point function is a function which is only specific to that point in space, right? So, what do you mean by what is rotating? After all, like population is not a point function. You say population of Delhi or population of IIT, okay? But population density is a point function. See, flux density is a point. So, what is phi with how do you find phi if you know B? B into area. So, you need to specify geometry, okay? So, flux per pole is understandable. A pole, I mean whatever flux that is given by the pole, then pole means you specify the area of the pole. It has a length, it has a diameter, or this thing, pole area. Similarly, MMF will be H into L, you need to length. MMF, like EMF, it is between you integrate H over length, then you have this, okay. Therefore, MMF has a meaning, because when you define MMF as the magnetic potential difference between stator and rotor surface radially, okay. So, you can always say, see, this is the MMF, let us say at this point in theta, some position theta or whatever it is. So, you can always say MMF is the magnetic potential difference, you see this is F. So, stator surface has some x, rotor surface has y, x minus y is the MMF at that point, okay, I mean at that radial distance, and MMF drop F will depend upon the gap also. If gap is more, MMF for the same H, for the different it will happen, okay. Similarly, when you say flux, right, so there will always be flux, isn't it? There will always be flux, but when flux rotating means the whole gamut is rotating, right. If a pole is rotating, if you rotate a pole, your whole flux will itself be rotating like that. I mean both have meaning and both have both are rotating, okay. So, in a 3-phase induction motor, air gap flux is constant, air gap flux is rotating. And how does the air gap flux come into picture? Okay. How do you, in any electrical machine, how do you have a air gap flux? Air gap flux is because you magnetize the stator surface, you magnetize the rotor surface, right, through putting conductors into the stator, into the rotor, passing currents in them, then you magnetize them, then the difference between them will be the air gap flux. F of the air gap will be whatever the magnetic potential of stator minus the magnetic potential of rotor, isn't it? That will be Fg between the stator and rotor, okay, and that will change with position depending upon the type of excitation that you have, okay. Now, so air gap flux depends upon, so air gap flux depends on Fs and Fr, right. Now, till now what was rotating? Okay. What was rotating was forward stator MMF was equal to backward stator MMF. This is the correct fact. Forward stator MMF, if you have a single phase winding, then you have Fs plus is equal to Fs minus. This is the correct situation. So, forward stator MMF is equal to backward stator MMF in a single phase motor, not the forward air gap field is not equal to backward air gap field. Why? I made both the statements. Forward stator MMF is equal to backward stator MMF. That is correct statement. But I say forward air gap flux, forward rotating air gap flux is not equal to backward rotating air gap flux. Why? Why is it so? Because of this rotor reaction. Because I have already told you flux is not only due to Fs, it is also due to Fr, is not it? The flux is also due to the rotor MMF. How the rotor is not a dead iron all the time. Okay. So, rotor MMF opposes the stator current, because there will be in any induction motor the short circuited squirrel cage bars, they get currents induced in them, okay, and this rotor surface also gets magnetized because of the induced rotor currents. Okay. Now the forward field, forward MMF will react in one way, backward MMF will react in another way. So, the rotor current induced due to forward MMF is not the same as induced due to backward stator MMF. So, forward stator MMF will induce in one way, backward stator MMF will induce another way. So, therefore, what will happen? This causes reduction in backward flux, because the rotor current induced due to backward field is larger, because the slip is larger for the same stator MMF, and therefore, the forward flux will be more. So, forward area flux will be more than the backward air gap flux at other speeds except in starting. Okay. So, therefore, the actual situation is that the forward torque is more than the backward torque than what was assumed earlier. Therefore, if you assume that the forward flux is same as the backward flux, it produces certain forward backward torque. Now, if you assume only forward MMF is same as the backward MMF, but the rotor reaction is different. Therefore, the forward flux will be more than the backward flux. Is it okay? Because rotor reacts differently for forward and backward fields, right. Therefore, this is a actual situation. Therefore, we have to modify the torque speed characteristics. We have to modify than it was earlier. Therefore, if this is the TF, which is not same as, not as in 3-phase motor, because the fluxes will go on changing at different speeds, whereas in 3-phase motor it was not changing, air gap flux was same in a 3-phase motor. Okay. So, that is, so you have a much better characteristics that way, and this is TF and this is TB. Okay. This is a modified torque speed characteristics which will have a better net torque but starting no problem, starting will be same, but the net backward torque. Okay. So, this is a situation that the forward MMF is equal to backward MMF in stator, but rotor forward MMF is not equal to rotor backward MMF, therefore, forward flux is not equal to backward flux. Okay. So, this is one thing you need to understand. So, this will be the net characteristics, still there is no starting torque. So, what will be torque at synchronous speed? What will be the single phase motor torque at synchronous speed? Is it 0? Huh? So, you will notice that there is a in fact, if you expand this, the net at synchronous speed there is a negative torque, slight. So, 0 torque occurs at slightly less than synchronous speed if you look at this curve. So, one other thing is it will happen like this. Okay. Okay. Therefore, I think we have to stop here because I think I have pushed in enough of confusion in your mind. Okay. You please think about it. So, next class we will look at the starting of what are the mechanism of starting of single phase motors. Okay. We will stop it here now. Okay. Thank you.